Howdy, I'm Austin Benedetti,
I'm Javier Mirabal.
And I'm Reed Pelasik.
and today we'll be giving our final presentation for our Pocket Diagnostics project. For a little bit of background on our project, the problem that we're trying to solve is that currently existing portable electrical measurement systems have limitations. For example, they are either wired, require Wi-Fi, or are dedicated to a single electrical measurement tool. So Pocket Diagnostics will provide a multi-purpose electrical measurements platform controllable through an Android application, and it will communicate with the measurements unit that contains probes through wireless Bluetooth communications.
Here we have the system overview. On the left, we see the 5 functions that the device supports. On the bottom, there is the onboard power supply. And then we have the microcontroller unit, which interfaces with all of the 5 systems. And the Bluetooth module, which the microcontroller uses to communicate with the Android mobile device.
Here's the overview of the Android application subsystem. On the left is a flow diagram for the application. From the home screen, the user can connect to a Bluetooth device or view the user guide if they need to know more about the Pocket Diagnostic system. After they've connected to a device, they can select a measurement system to use and transition into that activity that supports that subsystem. As this happens, the Bluetooth service class will be established and begin functioning. A few engineering design decisions that I had to make to meet all requirements include adding an end of message character for subsequent Bluetooth messages. A place where this is an obvious necessity is to parse messages that will be repeatedly received at a fast rate, such as in the oscilloscope or the logic probe. And I also made use of the activity lifecycle to manage the Bluetooth connection throughout the entire application. As a software design decision, I abstracted all Bluetooth communications out into a separate class containing those threads, just for good software design to not repeat code unnecessarily. And lastly, I set the application up to remember the last Bluetooth device that was connected to the application for the convenience of the user. This is the first slide displaying the results of the Android application subsystem. Verification and validation has taken place through a Bluetooth module connected to an Arduino microcontroller, and the Arduino is running a serial forwarding program that I wrote. So basically, any communication sent from the computer will be forwarded through the Bluetooth module and the Arduino and sent to the application, and any messages sent from the application to the Bluetooth module will be forwarded back through the microcontroller to the computer so that all communications can be seen within the Arduino IDE's serial monitor. On the top left is the home screen displaying the currently selected Bluetooth device, and on the top right is where the user can select the Bluetooth device to connect to from paired devices or other discoverable devices. In the bottom left is a part of the digital I/O activity. The top indicators are the inputs and the bottom indicators are the outputs. On the bottom right is what was sent from the Arduino terminal. So I/O was received from the Bluetooth module as the user or as the application transitioned into the digital I/O activity. From the digital I/O activity, the next thing I did for this demo was to select to set the digital outputs by hex string. I put in A9, and the respective bit string for A9 was displayed on the indicators and sent from the Bluetooth on the device to the microcontroller. Then I sent 1001, 0110 from the serial monitor to the application, and it is displayed on the indicators for digital inputs. Lastly, and this will be seen in all sub activities, the EX message is the message that will be sent to from the application to the MCU to let the MCU know that it is exiting that subsystem. These are the graph-based subsystems. Currently, they display sample data based on a Bluetooth input. The graphs will only update when the play button is selected, and both graphs support zooming by pinching in either the direction of the x-axis or the y-axis. The logic probe has indicators that show whether the signal is high or low, and the waveform reflects that signal. And the oscilloscope supports sine and cosine wave for each of the two channels. On the right, for the oscilloscope, you can see channel 1 sine will display a sine wave from channel 1, which is blue. Channel 2 cos displays a cosine wave on channel 2, which is red. And these signals can be toggled on and off. And again, this can be scaled in the direction of the x or y axis for the user to focus in on the part of the graph that they wish to. On this slide is the voltmeter and the serial data sniffer. The voltmeter displays the voltage that is coming in from the MCU. If it is between -1 volt and +1 volt, it will display in millivolts. It'll change the units. For the serial data sniffer, upon initialization, you can see that it sent the message DS for the data sniffer, and then it initialized the baud rate at 300. For this demo, then I changed the baud rate from 300 to 115.2K. And I sent 4 messages that are each displayed in the TX and RX. And the way the application processes that is with a TX or RX header to know where to put the message. As these text boxes fill up, the user can scroll within the text box to see older messages and get back down to the newer messages.
Now, moving on to the digital components of our design, I'll start off with an overview of them. On the left, in the green, you can see all of the inputs to my digital circuitry. Next to them in the yellow are any special conversion circuitry necessary to interface between the inputs and the main microcontroller. Between the special circuitry and the main microcontroller, I have listed the protocol that will be used to communicate between the inputs and the main microcontroller. Next to the main microcontroller, I have the Bluetooth module, which the main microcontroller communicates with over UART, and between the Bluetooth module and the Android device, they communicate via Bluetooth 2.0 serial port profile. So with regards to the digital interfaces between my subsystems and Austin subsystems, as well as my subsystems and Javier's subsystems, for the Bluetooth module, I have currently successfully programmed it to pass data between the main microcontroller and the computer. The Bluetooth module communicates with the main microcontroller via UART at 900 kilobauds, and the Bluetooth module communicates with the computer via Bluetooth 2.0 serial port profile at 921 kilobauds. With regards to the ADCs, I'm currently writing programs for the MSP432, which will be finished by demo, although unfortunately I will not have any physical hardware to demo, both due to the fact that we have changed the ADCs that we're using several times, and the fact that the ongoing situation prevents us from acquiring the hardware as easily as we would have. With regards to the digital diagnostics tools that I'm in charge of, with the Logic Probe, I have assembled it and tested it in conjunction with prototype interface and initial MSP432 program, and it works successfully. With regards to the serial data sniffer, I have also written an initial program for it and tested it, and it also works successfully. And with regards to the digital I/O, I'm currently finishing the program, and we'll test it this week. With regards to all 5 of my subsystems, I'm currently finishing the programs and debugging them and adding any missing features. So I will have them ready in time for demo.
All right, finally for the analog subsystems, here we have an overview to get a lower level look into each subsystem's operation. We can see that both the oscilloscope and the voltmeter have a differential input hooked up to the differential amplifiers in the first stage. The oscilloscope has a low-pass KRC filter, and both the oscilloscope and the voltmeter have analog to digital conversions handled through the use of specialized chips. At the same time, the power subsystem at the very bottom uses two different components to convert the voltage level from the 8 AA batteries to +5, +3.3, -5, and -3.3. So moving on to the simulation results for the oscilloscope. At the very top is the magnitude frequency response. We can see the low-pass filter behavior of the KRC filter with a pole at around 1.3 kilohertz, which is around where we want it to only accept signals of 1 kilohertz or less in frequency. At the bottom, we have the transient waveform. We have the differential input in red, and we have the output in green. The output is reduced by a factor of 2 due to the ADC's input range being half of the overall total system input range, which explains the discrepancy between the red and the green amplitudes. Moving on to the power supply simulation, the input range goes from 3.2 volts to 6 volts due to battery charge and discharge. But as you can see, due to the components selected, the output is unchanged. In this case, it's the +5 volts output. The +3.3 volt output has uses the same component, only a little bit different feedback circuitry to get essentially the same result. And then here we have the -5 volt simulation. As you can see, no matter the input within the valid range, the output is at -5. And again, there is also a -3.3 volt supply that operates almost identically over the same input range. Finally, we're moving on to the layouts. Both of the layouts that are completed are rough drafts. The outputs and inputs are still unconnected, and both will be improved and more polished by demo next week, and then again over the summer. So here we have the oscilloscope PCB layout. And then in the next slide, we can see the voltmeter PCB layout, which thanks to the chip being used and the lack of the filter is overall less complex than the first one.
So in conclusion, compared to our execution plan for this spring, the Android application successfully sends and receives Bluetooth messages with dynamic UI reactions for all 5 subsystems.
The microcontrollers will successfully read, process, and transmit desired data correctly.
And the analog subsystems simulate accurately and will have layouts completed.
So our integration plan for the summer and for the fall is during the summer, I will combine the MSP432 programs into one larger program. I will choose a case with a battery compartment to house the PCB from PackTech enclosures. Javier and I will work together to finish and optimize the initial PCB layout, and Austin and I will work together to finalize Bluetooth packet structure for each subsystem's data. Moving on to the fall, Javier and I will work together to populate and test the PCB, then make necessary adjustments to its design. and Austin and I will test communications between the microcontroller and the Android application.